All right, so today's research talk, I'm going to introduce some work that Claire and I did earlier on this year on a new numerical method for the linear rheology of living polymers. For those of you who have not heard me talk about living polymers before, the idea of a living polymer is a system of polymers where the polymerization reactions are reversible and hence non-terminating, and therefore in some sense still alive at long times, compared to terminating polymerization reactions proceed to a point and then proceed no further. So the molecular weight distribution for a living polymer system is in some sense dynamic. Long chains are always breaking apart into short chains are always attaching up to become long chains. And it turns out that there is an effect of a coupling between the polymerization reactions and the stress relaxation kinetics in these materials. So this, we're going to go over a brief history of the work that's been done on this in terms of the modeling. The first work that was done on this coupling between reversible scission kinetics and stress relaxation processes was done now almost 40 years ago by Mike Cates. And he put together a stochastic model where he treated the reptation process as a one-dimensional random walk on a platform. And then the reversible scission processes were different ways of updating the length upon which the random walk was occurring. And of course, depending on the length of the platform, the speed of the random walker changed as well. And through these simulations, he was able to capture and explain the effect of reversible scission reactions on accelerating stress relaxation kinetics in living polymer systems. The most common chemistry for living polymer systems is worm-like micelles. So at various points in this talk, you may hear me interchange living polymers and worm-like micelles because worm-like micelles are a common class of living polymers. I'll say a bit about what worm-like micelles are. Worm-like micelles are commonly found in a lot of hand soaps and shampoos. They are self-assembled surfactant molecules of a very specific sort of shape. They happen in very specific salinity for the surrounding aqueous media. And the preferred self-assembly structure for these surfactants is not spheres or sheets, but rather ropes. The hydrophobic parts all form the core of the rope, and the hydrophilic parts form the exterior of the rope. These ropes are held together by van der Waals interactions, and so it's basically KT per monomer that keeps these things together, and thermal forces are sufficient to break them apart, unlike covalently bonded polymers where you have hundreds of KT per bond, and those things don't really degrade just sitting around at room temperature. Okay, so the initial work was done by Mike Cates almost 40 years ago. He put together a stochastic model that captured the important things that people wanted to capture. Around the same time, a guy named Lequeux in France put together a different approach that was not stochastic but rather deterministic. And his idea was saying, well, if you have things changing size, the group size of which a piece of material is attached to, and different group sizes relax their stress at different rates, then there's this coupling between the population balance equations and the stress relaxation equations that effectively amounts to putting population balance terms inside of your stress relaxation equation. It was a brilliant insight, but there were a few problems with the execution, and the math was absolutely monstrous, and so it was largely lost to history, despite the fact that the insight was fundamentally good. It was too complicated to work with, and it gave answers that were known to be wrong, so nobody used it. Shortly after that, Granick and Cates put together, so this is the same Cates from the original work, they put together something called the Poisson renewal model that on the surface here, this equation that defines the Poisson renewal model is monstrously complicated, but after applying a Laplace transform and doing a bunch of math that I guess people in the quantum mechanics space don't mind doing, it all simplifies down to something very, very clean. And it did a good job of fitting and explaining the worm-like micelle data, but it was definitely not attempting to replicate in detail the reversible scission process. It came up with a convenient approximation of the reversible scission process that is not very well understood necessarily, their approximation. Okay. Then for a long time, there was no further major model developments. What I would say the next major model development was this work by Zhu and Larson in 2014, where they put together this thing called the pointer algorithm. And the pointer algorithm was basically the same one-dimensional random walk process that Cates put together in 1987, but it was sort of like a computer science upgrade version. So they wrote it in a very efficient computer programming language, and they did this thing where they said, instead of one random walker going through all of these loops and iterations, we're basically going to keep track of, one random walker basically represents one individual segment on a chain, right? They said we're going to keep track of, instead of individual segments on the chain, we're going to keep track of whole blocks on the chain. And that whole block is a large number of individuals. So basically they found a way of accelerating the simulations, reducing the sampling error, right? And they were using this in order to fit experimental data and extract quantitative information about what is the reptation time, what is the breaking time, what is the chain length. And they released this algorithm open source for people to use, and it was a major step forward compared to what had existed previously. Because compared to the Poisson renewal model, they were actually modeling the reversible scission process. Now, in 2020, during my postdoc, I worked with Mike Cates again, and we put together a set of equations, that's probably Ramesh, you can let him in, that described the reptation and reversible scission in sort of the same terms as Lequeux, using population balance type equations, but instead of relying on a single mode description of reptation, we kept the full chain description of reptation. Those equations, though you'll see them on the next slide, look sort of monstrously complicated. And so during the course of my postdoc, I couldn't find a good way to solve them, which I'll also elaborate on. And shortly after I wrote these equations, I came up with an approximation of them that in the end turned out to be equivalent to the Granick and Cates Poisson renewal model. So if you don't like the look of the quantum mechanics-y explanation of Poisson renewal that Granick and Cates puts forward, you can rely more on the PDE heat equation type expression that we developed more recently, because the two forms are ultimately equivalent. Okay. The core problem here, up until just recently, was that if you wanted to model the true reversible scission sequence rearrangement process and not some approximation like shuffling or Poisson renewal, you were stuck with a stochastic method. We had the equations to treat it as a PDE problem, but we did not have a satisfying numerical method. Now, if we have the equations, what's so hard about coming up with a satisfying numerical method? Okay, we'll get to that. I forgot my order of my slides here. But first I want to do a bit of review on tube theory. I've talked about reptation and reactions. I think it's pretty intuitive to think about polymers breaking apart and attaching as the relevant reaction processes. But if you're not familiar, what do I mean by reptation? Well, what I mean is that you have a polymer, which you can think of as a long spaghetti noodle in a melt of other spaghetti noodles, and the surrounding noodles prevent it from moving laterally, but it can slide back and forth along its own contour. And that process of sliding back and forth along its own contour is ultimately a one-dimensional diffusion process, and it is the main way by which the polymer is able to relax its stress. Once it's diffused out of a tube segment, it won't diffuse back in. Any memory of deformation history associated with that tube segment is lost, and therefore the stress associated with that tube segment is lost. Because it can be represented as a one-dimensional diffusion process, you can write it out as a one-dimensional heat equation in terms of a probability, P, that a tube segment at contour position S, you can index the contour of the chain from S equals 0 to S equals L, where L is the full length of the chain. And you can keep track of the tube survival probability at any contour position as a function of time. And the initial condition is that the probability is 100%. If it was there initially, it's still there initially. But at the very ends of the chain, you're always sort of at the boundary of the open air. You're always relaxed. You're always seeing the outside of the tube. And we all know how to solve the one-dimensional heat equation. So that's fine. But the problem is, when you attach these population balance terms to the end, it no longer looks very much like an ordinary heat equation. The population balance terms sort of take over. And just because you know a numerical method that works for the heat equation doesn't mean that it's going to be cleanly compatible with the reversible scission reaction terms once those get added in. I'll go term by term to describe what each of these is representing here. On the left-hand side, at the beginning, we have the rate of change of tube survival at some time t and some contour position s for a chain of length L. So now we're indexing the chain lengths from 0 to infinity, right? There's no lower chain length that we're considering and no highest chain length we're considering. A chain could theoretically be found at any possible length. That's the equilibrium of this reversible scission reaction. Okay, so it's some time evolving process for the tube survival probability. The first term on the right-hand side is this diffusion process. It's a reptation process, and we have a 1 over L dependency. The longer the chains are, the slower the reptation process will go. Then we have the reaction terms by which a chain of length L disappears. A chain of length L can disappear if it breaks apart into two shorter chains. Note that the rate of breaking increases as the chain gets longer. It just has more places to break. Or a chain of length L can disappear if it becomes longer than length L by combining with another chain around it. Okay? That recombination rate is independent of length, it turns out. Then we have the next two terms that are the appearance of chains with length L. A chain of length L can appear if two shorter chains attach together to make a chain of length L, or if a longer chain breaks off a fragment of length L. I got these backwards when I talked about them. This is actually the recombination, and this is the scission event. You can demonstrate this schematically here. If I have chain 1 and chain 2 being added together, then the product chain is going to have a tube survival probability distribution that is simply the appended tube survival probabilities of the reagent chains. In the reverse, if I have a long chain that breaks apart, and I define this vertical gray line as the place where the chain breaks apart, I'm simply going to split the tube survival probability of the parent chain into the daughter chain fragments. Right? Visually, schematically, this makes sense. When you try to write it down as an equation, this simple picture becomes very nasty because of the way that appending and splitting works mathematically. It just is ugly. It's an ugly operation mathematically. It's a clean operation visually. Okay, so when you have a set of equations to solve, you just need to solve them. You don't care if it's particularly elegant or efficient. The first thing you might think to do would be finite difference equations of some sort, right? But I don't want to have finite difference equations where I set up the same discretization, uniform discretization across my chain. That seems like wasted space. What I want to do is I know that my tube survival probability is going to be changing most near the ends because that's where it has to reconcile this, zero probability to finite probability exchange, right? The chain ends in especially fast breaking and recombining systems are where the stress relaxation gets localized, and I don't want to waste a lot of computational energy solving for interior points where the solution isn't changing a lot, okay? So if I'm going to use sort of a finite difference-based method, I want an adaptive discretization of my equations. The problem is, and by the way, with this adaptive discretization, I can handle chain scission just fine. If a chain breaks apart, then I can split it at any one of those nodes and project it onto the longer or shorter chain length distribution, and I'll have enough information. I won't have lost any information anywhere, right? The problem comes with the recombination. So, for example, if I have, in the second case, two shorter chains of equal length combining to make a chain of longer length, what I have to do with a finite difference type method is I have to do some type of linear interpolation to make sure that I project the information from one discretization onto a different non-commensurate discretization. The problem is that my short chains have a bunch of information in places where my long chain solution is expecting no information. And so when I project the information that I have onto the information that I need, a ton of it gets lost, gone forever. So this idea of conserving tube segments is out the window. I can't conserve tube segments in this way. The other problem is that if I have an asymmetric combination of a short chain plus a longer chain, where the dip in the tube survival probability occurs in a gap between 2 points, then that gap will also get missed. So in the first case, I'm undercounting tube segments. In the second case, I'm overcounting tube segments. And there really is not a clean way to fix it. You can sort of fix it by accepting to have very high resolution everywhere. But then you also want to sort of make sure that you have the same resolution at different chain lengths so that you don't have to deal with non-commensurate meshes for chains of different sizes and those linear interpolation processes. But I mean, I think you can see that this would all just become a huge mess if you tried to do it with a finite difference method. You could probably figure it out, but it would be like a 1 million by 1 million matrix equation that you're trying to solve because of all of this extra resolution that you have to put everywhere to keep things clean and simple. And I'm not going to solve a 1 million by 1 million matrix equation. It's not going to happen. So what I said is, I gave up on this problem for a very long time. And then I started teaching 101B, the heat transport course at UCLA, to the undergrads, and I kept teaching them and hammering home that Fourier solutions are the way to solve the heat equation. And I thought to myself, you know what, I can't keep teaching them this without at least trying a Fourier solution for these reversible scission equations. So I assumed the existence of a Fourier series expansion that would help resolve the solution in the contour direction, right? So for any given chain length, there is a Fourier series expansion in the contour position that will tell me how the tube survival probability is varying along the chain length for that particular length of chain. So I set up this Fourier series expansion, and I plug it into my governing PDE equation for the tube survival probability. And when I first did this, I said, oh, this looks terrible. My spidey senses are going off and telling me this is not going to produce anything useful. But I said, no, let's finish it. Let's see, we've come this far. Let's see what this actually gives us. And after rearranging and consolidating terms, you end up with something that's actually very clean. The dynamics of the tube survival probability can be projected onto the dynamics of a set of Fourier coefficients, and you have a linear relaxation term corresponding to reptation here and the loss of chains by scission and recombination. And then you get this sum inside of an integral of different mixing terms that describe how information moves around due to the recombination events. Okay? And the piece inside of this, I can do a sum inside of an integral. I can do that as long as what I'm the argument of what's inside the sum and the integral is something that's clean and simple and straightforward to evaluate. And it turns out that it is. It's just this function that has a few different values depending if L is greater than or equal to M, and if M is equal to or not equal to N. So these edge cases are pretty easy to deal out, but it collapses to something that actually looked, to me, surprisingly clean. So we wrote up a numerical method to implement this method and solve it. But to do that first, if you've got an infinite sum inside of an infinite integral, the first thing that you need to do is choose a proper discretization strategy. You need to choose a cutoff mode in your Fourier series, and that cutoff mode can vary with chain length. There's no need to keep the same cutoff mode everywhere. And you need to discretize in length in order to perform the integral operation. So with the discretization in length, a couple of considerations. We need to make sure that our shortest chain length represents chains that reptate much faster than they break. Otherwise, we're missing pieces of the stress relaxation picture. And we need to make sure that if it's a slow relaxing system, the longest chains that we keep track of capture the slowest relevant relaxation processes. It turns out with a exponential molecular weight distribution and a reptation process that varies as length cubed, you need to keep chains out to, say, for example, less than 1% of the molecular weight distribution, because those are really important to the stress relaxation. They represent much more than 1% of the stress relaxation. Okay, then in regards to the Fourier mode cutoff, this is a place where this method really shines, because each Fourier mode corresponds to a defined time scale for its relaxation process, for its reptational relaxation process. And what we're able to do is choose a resolution time scale and say for processes occurring faster than, say, 10 to the minus 4 seconds, I don't care if my numerical method resolves those accurately or not. It just has to resolve everything slower than that. So we choose our cutoff time scale to be much faster than the breaking time scale, which is the fastest physical time scale in our problem. As long as our cutoff time scale is much, much faster than our fastest physical process, we should be able to get a good physical representation of the dynamics of this problem. So now we have a cutoff mode that's chosen efficiently and effectively everywhere across our system. And once this is discretized, it just becomes a linear matrix equation. And the linear matrix equation is diagonalizable. For those of you that took 260, the non-Newtonian fluid mechanics class with me, you may have remembered how I talked about the Rheology model and how it was set up as this big matrix equation that was then diagonalized into orthogonal modes or whatever, and then you could solve it analytically in this way. And the diagonalization process gave you the relaxation spectra, the relaxation times, in this case tau n, and the weights corresponding to each of those times, the WNs. If you have the relaxation spectra, the times and the weights, it is trivial then to calculate the complex modulus or the relaxation modulus. And we will do both of those. Okay. So the first step is to validate the method. We've got two different ways of validating it. First of all, we mentioned before the shuffling model, which is an analog of the Poisson renewal model. The shuffling model we've recently found actually has an analytic solution. So we can put on the board the analytic solution, and we can approach the starting PDE with the same Fourier series decomposition. We can choose a cutoff time scale, in this case 10 to the minus 2, and we see that the frequency at which the numerical solution starts to diverge from the analytic solution is indeed matching to our time scale of 10 to the minus 2, right? A frequency of 10 to the positive 2 denotes a time scale of 10 to the minus 2. So the analytic solution and the Fourier series constructed solution depart only at the point where we set our cutoff time scale. So we are fully in control of where our numerical solution will depart from the true solution to our problem. That's important. That's great. But this is for the shuffling model. We'd really like to independently have some way of validating this for the true reversible scission model. So what we do there is we take some calculations for the pointer model. The pointer model is pretty good at calculating a relaxation modulus, G of t, but it does struggle more with calculating the complex modulus, G star of t, because that inverse Fourier transform is sort of an ill-conditioned problem, or the Fourier transform is an ill-conditioned problem. Okay. So what you'll notice here in the comparison, we set up both of these with the exact same value of zeta, the exact same reptation time, whatever. And the solution, the dashed line, is the pointer model calculation, and the solid line is our partial differential equation solution with the Fourier modes. And you'll see that by and large, the two are in fairly good agreement. but there's a bit more noise with the pointer model calculation, and at long times the noise gets a lot larger. The reason the noise gets larger at long times has to do, I believe, with the normal statistics of sampling systems at small numbers. So you start out initially with, let's say, 10,000 tube segments to resolve whether they're relaxed or unrelaxed. After 20 reptation times, you have about 1% of that left. You'll have 100 of these things left. At short times, your variability is going to scale as root n, right? So if you have 10,000 chains, your variability is the square root of 10,000, so you're looking at 100 chains out of 10,000 or 100 tube segments out of 10,000 that represent your potential variability, right? At long times, you've got 100 segments left, and your variability is the square root of that, so that's 10. So there's a lot more noise in the data as you get to longer times, but also, when you're trying to fit the relaxation spectra, the long time behavior of the solution gives you a huge amount of the information that you're actually interested in. So there's this problem that some of the most valuable information is coming from the data that is the most unreliable. And we have seen in the past, when using the pointer model, that if you just feed it the exact solution, for example, of the reptation modulus, or of the complex modulus for the reversible scission process, or something very close to it, and it should find a value of zeta equals 10 for a good fit, it'll find something else within the factor of 2, for example, right? So there's this uncertainty that is inherent to a stochastic process and this fitting procedure that it does, this nonlinear regression. There's uncertainty in the fit parameters, which was previously not possible to quantify because you didn't have a ground truth to compare against for those fits. But now we do, which is good. So now what I want to show here is a comparison of the shuffling model versus the scission model. This is something we tried to do in a previous paper using the Poisson renewal model as a means of representing the reversible scission processes. But here we see that with the same value of zeta and without adjusting the defined reptation time or complex modulus or shear modulus or anything, we're seeing very similar results. Previously, we were finding we needed large updates to parameter coefficients and all of that, but now we don't see that. It really looks like the shuffling model gives a very good approximation of the scission model without any update to its parameters. And remember, we have an analytical solution to the shuffling model. Okay, so to summarize and discuss future directions, we've developed a new numerical method that's reasonably fast. It takes about 5 minutes to generate a complex modulus for the simulations that we've reported here. Sometimes it only takes a matter of seconds. It just depends on the value of zeta in particular and your minimum time scale cutoff that you choose and so on. We've validated this in two different ways, by both comparing with an analytic solution and by comparing with stochastic solutions. And overall, the calculations from this reversible scission model look very similar to the shuffling model or the Poisson renewal model with no parameter changes. There's some drawbacks. This method is still slow compared to, obviously, an analytical solution, and it has poor scaling when there are really strict accuracy requirements. So the 5-minute simulation could very quickly go up to a 5-hour simulation if you were significantly more strict about your error tolerances. We also don't have a great way of introducing CLF yet. We have some ideas, we think they'll work, but we haven't implemented them yet. Implementations for the reptation and reversible scission method presented here, we don't expect you to write that from scratch. In our JOR paper, we have provided implementations of this method in both C++ and MATLAB if anyone is interested to try this out for themselves. We've also got some future directions that we're interested in exploring, but we can talk about those later in the interest of time. So with that, I'll do my acknowledgement slides, close the talk, and we are at just about 30 minutes on the dot. All right, this was again a practice talk for SOR 2024.